Somewhere in northern China, on a stretch of track about 4 football fields long, a 1-ton metal capsule just did something that should not be possible. It went from a dead stop to 700 kilometers per hour in 2 seconds flat, which is faster than a commercial airplane lifts off the runway and faster than a bullet leaves a pistol. And it happened on the ground, on a track, with magnets. The capsule moved so fast that if you blinked, you missed it. And by the time the engineers at the end of the track checked their instruments, the thing had already come to a full stop. Safely, under control, on a track shorter than some airport runways. And here is where the story takes a turn that nobody expected. 6 months later, the same team pushed a capsule to 800 kilometers per hour on a slightly longer track, covering the distance in 5.3 seconds. The real question you should be sitting with right now is a simple one. If China can pull this off and keep getting faster, then the reason America is still arguing about whether to build a single high-speed train between 2 cities becomes very hard to explain. Remember that question, because by the end of this video, the answer is going to make you uncomfortable. This is not just about trains, it is about you. It is about how you get from one city to the next, and whether your country is building the future or watching someone else build it. Right now, the fastest train in America tops out at 160 miles per hour, which comes out to about 260 kilometers per hour, and it only hits that speed on a tiny stretch of track between Boston and Washington. The rest of the time, it crawls along at much lower speeds because the tracks are old and shared with freight. China already runs regular passenger trains at 350 kilometers per hour every single day across more than 50,000 kilometers of dedicated track. That number represents more than 2/3 of all the high-speed rail on the entire planet, concentrated in one country. And now they are testing machines that go twice as fast as their current trains. If you find this as wild as I do, go ahead and hit that like button and subscribe if you have not already. What I am about to walk you through is one of the biggest technology gaps between 2 countries that most people have never heard of. And by the end, you are going to understand exactly how it happened and what it means for the way you travel. To understand why this 700 km per hour test matters, you first need to understand one thing about how trains work. And I promise this is simpler than you think. Every train you have ever ridden, every subway, every commuter rail, every Amtrak works the same basic way. Metal wheels sit on metal rails, a motor spins the wheels push against the rails, and the train moves forward. That system has worked for almost 200 years, and it is genuinely great at what it does. The problem shows up when you try to go really fast. When metal wheels touch metal rails, they create friction, which is that same resistance you feel when you rub your hands together quickly. The faster those wheels spin, the more friction builds up. And more friction means more heat, which means more wear, which means the wheels and the rails start falling apart. And there is a wall that every train eventually hits. Once you climb above about 350 or 400 kilometers per hour, the wheels spin so fast that the whole system starts to break down. The wheels vibrate, the noise becomes enormous, and the energy you need to push through all that resistance shoots through the roof. You are basically fighting the track itself at that point. That is why the fastest regular trains in the world, the ones running in China, Japan, and France, all top out around 350 kilometers per hour. Not because the engines lack power, but because the wheels cannot handle anything faster. The physics will not allow it. And that is exactly what led engineers to start asking a completely different question. What if you could get rid of the wheels entirely, and instead of rolling on the track, the train floated above it? That idea carries a name, and I want you to remember it, because it keeps coming back in this story. The word is maglev, short for magnetic levitation. Levitation just means floating, and magnetic means it uses magnets to do it. The concept is beautifully simple. You put powerful magnets on the bottom of the train, you put matching magnets on the track, and you arrange them so they push each other apart, the same way 2 magnets push away from each other when you try to press the same ends together. You have done that with fridge magnets, and this is the same idea scaled up to the size of a train. That pushing force lifts the train off the track, Not by a lot, just a few centimeters. But that tiny gap changes everything. There are no wheels touching the rail, no friction grinding things down, no contact at all. The train floats on a cushion of magnetic force, like a hockey puck gliding on an air hockey table. And without friction holding it back, you can push it much, much faster. But here's the thing most people never hear about. Making a train float was only half the challenge, and the other half turned out to be even harder to solve. Maglev is not a new idea, and getting the history right matters here. Germany started working on magnetic trains back in the 1960s, and Japan has been building and testing maglev trains for decades. Back in 2015, a Japanese test train clocked 603 kilometers per hour with real people on board, and that record stood for years. China already runs a working maglev line in Shanghai that opened in 2004 and carries real passengers from the airport to the city center at over 400 kilometers per hour. You can ride it right now if you buy a ticket, sit down, and watch the city blur past your window. So the obvious question becomes, what makes this 700 km/h test different from everything that came before? And the answer comes down to what China actually proved on that short track. They did not just prove you can float a train. Everybody already knew that part. What they proved is that you can accelerate a floating object to nearly the speed of a commercial airplane in the time it takes you to say the word go, and then stop it safely on a track shorter than some highway on-ramps. That is not a train test, that is a physics test, and the physics worked. Here is what actually happened, because the details matter more than the headline. A team at a research center called the Donghu Laboratory in Hubei province built a special track. For the first round of tests, that track ran 400 meters long, which is about a quarter of a mile, roughly 4 football fields laid end to end. They placed a capsule on that track weighing about 1.1 tons, roughly the weight of a small car. Not a toy and not a scale model, but a real heavy piece of metal and magnets and sensors. Then they turned on the system. The capsule floated off the track, and a series of electric coils built into the track itself created a wave of magnetic force that pushed the capsule forward. Think of it like a surfer riding a wave, except the wave is invisible, made of magnetism, and moving at the speed of a jet airplane. In 2 seconds, the capsule hit 700 kilometers per hour. Your car takes longer than that to go from 0 to 60 miles per hour. And this capsule went from 0 to faster than a Boeing 737 at takeoff in 2 seconds on a track you could walk from end to end in about 5 minutes. And what came next might be even more impressive than the speed itself. The capsule had to stop on that same short track, and it did, coming to a full, controlled stop in about 200 meters, which is less than half the length of the track. The forces involved are hard to picture. The capsule pulled about 10 Gs of acceleration, which means the force pushing it forward was 10 times the pull of gravity. Fighter pilots trained for years to handle 9 Gs without blacking out, and this capsule handled 10. Every system held together under those forces. The magnets kept the capsule floating. The guidance system kept it centered on the track to within 1 millimeter, which is thinner than a credit card. The braking system brought it to a dead stop without a single failure. And nobody should put passengers on a 10G ride, because that would flatten a person into their seat. This was a stress test designed to answer one question, which was whether magnets, motors, braking, and guidance can all work together at extreme speed. The answer came back yes. 6 months later, the same team ran the test again on a longer track, this time 1 kilometer, and pushed the capsule to 800 kilometers per hour in 5.3 seconds. That is faster than any maglev vehicle has ever traveled anywhere in history. There is that word again, maglev, and every time it shows up in this story, the speed keeps climbing. But the speed record itself is only half the story, because what another team was doing at the same time sent a signal to every country and company paying attention to the future of transportation. While one team launched capsules on short tracks, a separate Chinese program was doing something even stranger. They were putting a maglev train inside a giant sealed tube and sucking the air out of it. And the reason is simple. When you are floating on magnets, you have eliminated the friction from wheels touching rails, which is great, but there is still one more force slowing you down, and that force is air itself. Think about sticking your hand out the window of a moving car. At 60 kilometers per hour, the wind pushes your hand back gently. At 120, it is hard to hold your arm steady. At 300, the force is enormous, and your arm would fly backward. Air resistance acts as an invisible wall that limits how fast even a maglev can go in the open. Once you pass about 600 or 700 kilometers per hour, the energy you need to push through the atmosphere becomes so extreme that the whole system stops making sense. You are basically trying to punch a hole through the sky with every meter of forward motion. What if you remove the air from the path entirely? And that is exactly what the T-Flight project set out to do. Built by a company called Acela, which happens to be China's biggest missile manufacturer, so they know a few things about moving objects very fast. The T-Flight is a maglev capsule that runs inside a sealed tube. They pump most of the air out of that tube, creating something close to a vacuum, like a version of outer space laid flat on the ground. No wheels, no friction, and now almost no air resistance. On a 2-kilometer tube in Shanxi province, the T-Flight clocked 623 kilometers per hour, which landed it faster than any maglev vehicle had traveled anywhere on Earth at that time. And they pulled off that speed on a track you could walk from one end to the other in about 20 minutes. The next phase calls for extending that tube to 60 kilometers, and at that length, the team expects to reach 1,000 kilometers per hour, which is faster than the cruising speed of a passenger jet flying overhead right now. You would board a capsule in one city, the door would close, pumps would pull most of the air out of the tube, and then magnetic forces would launch you forward at airplane speed, except on the ground, with no turbulence, no runway delays, and no jet fuel burning above your head. None of that is a metaphor, that is the actual engineering plan, and they have already tested the first working version. And what makes this even harder to ignore is what is happening in the rest of the world at the same time. Japan runs its own maglev project, the SC maglev, which is supposed to connect Tokyo and Nagoya at 500 kilometers per hour. But the project has been stuck for years because of environmental disputes in one region, and the opening date has slid from 2027 into the early 2030s, possibly later. Europe had maglev research programs decades ago, and Germany actually invented one of the first commercial maglev systems, the same technology that Shanghai bought and still runs today. But Germany never built a maglev line for its own citizens, and the program faded. The United States currently operates 735 kilometers of what it calls high-speed rail, which is Amtrak's Acela running between Boston and Washington. Its newest trains top out at 160 miles per hour, about 260 kilometers per hour, and most of the time they run much slower because the tracks are old, shared with freight trains, and full of curves that force the train to brake. Compare that to China's 50,000 kilometers of dedicated high-speed track. That is not a gap, it is a canyon so wide you cannot see the other side. And the experimental capsule tests are not happening in a vacuum of ambition with no real-world backing. China recently tested a new conventional train called the CR450, a wheeled train running on normal rails with no magnets involved. During test runs, that train hit 453 kilometers per hour. And when two CR450 trains passed each other going opposite directions on parallel tracks, the combined relative speed came in at 891 kilometers per hour. That is a wheeled train passing another wheeled train at a combined speed close to the speed of sound on regular upgraded track. And passengers are expected to ride it by 2030. You have to understand the scale of what is unfolding here, because this is not one isolated project. This is a whole country running multiple speed programs at the same time. Conventional trains keep getting faster. Maglev trains are being prepared for commercial routes that could cut the Beijing to Shanghai trip from 4.5 hours to roughly 2.5. And vacuum tube capsules keep breaking their own records every few months. All of it is happening at once. One insider in the global rail industry put it plainly: when your main competitor spends more on rail than the rest of the world combined and tests technology that nobody else has gotten to work, you do not have a gap, you have landed in a different race entirely. Now I have to be straight with you, because there is a real and serious difference between a test on a short track and a train you can actually buy a ticket for. That 700 km/h capsule weighed 1 ton, but a real passenger train weighs hundreds of tons. Scaling the magnets, the power systems, and the track to handle that much weight at that speed is a massive engineering problem that nobody has solved yet. The vacuum tube faces its own version of the same challenge. Keeping a 60-kilometer tube sealed and pumped down to near vacuum is incredibly difficult because one small crack or one failed seal lets the air rush back in, and at 1,000 kilometers per hour, that could turn catastrophic in a fraction of a second. And then there is cost, which might be the biggest obstacle of all. The existing Shanghai maglev line cost roughly $50 million per kilometer to build. A vacuum tube system would cost far more than that, and even China, with its enormous rail budgets, has not committed funding for a full-scale commercial vacuum maglev line. Safety regulations, land rights, power supply, and earthquake resistance all sit on a long list of problems that do not care how fast your test capsule travels. None of these challenges erase what the physics showed on those test tracks. They define the gap between what works in a controlled lab and what works when you are carrying 1,000 passengers between two real cities. And that gap is very real. But here is the pattern that matters. Every generation of fast trains faced a version of this exact same gap. When Japan launched the first bullet train in 1964, critics said it would never be safe enough, never affordable enough, and never attract enough riders. And they were wrong. When China started building high-speed rail in 2008, the world said it was too ambitious, too fast, and too risky. And by 2025, they had more high-speed track than every other country on Earth combined. The pattern runs the same way every time. First comes the science, then the engineering, then the money, then the line on the map. And that brings us back to the question I planted at the very beginning of this video. If China can do this and keep getting faster, then the fact that America is still stuck demands an explanation. The answer has nothing to do with technology. America has brilliant engineers, it has the money, and it has the cities that need connecting. The answer comes down to choices. China made a decision decades ago that fast trains would become a national priority. Not a state-level project, not a private company's gamble, but a national mission backed by the full weight of the government. They built the tracks, trained the engineers, funded the research, bought the land, and connected the cities, year after year after year, even when individual lines lost money, even when critics called it wasteful. America made a different set of choices. It chose highways and airports, cars and planes, and those were great choices for the last century, but the world around those choices is shifting. Energy costs more every year, airports grow more crowded every season, and the distances between American cities land in exactly the sweet spot where fast trains outperform everything else. New York to Washington sits at 360 kilometers. Beijing to Shanghai stretches 1,300 kilometers. China runs a train between those two cities in 4.5 hours at 350 kilometers per hour, and the country is now building technology that could do it in 2. Against that backdrop, the fact that there is no train option at all between Los Angeles and San Francisco, a 5-hour drive, gets very hard to explain. This is bigger than trains. This is about which countries are willing to build the next generation of how humans move from place to place. And right now, one country is testing floating capsules at 800 kilometers per hour, while another is celebrating a new train that runs at 160 miles per hour on tracks that were laid down before most of the people watching this video were born. The world that ran on highways and short-haul flights did not announce its own ending. It just started losing ground, quietly, steadily, kilometer by kilometer, to something faster, something that floats, something built by people who decided to spend the money before anyone else was ready. When I started researching this story, I thought it was about a speed test, a cool number on a short track. But the more I dug into it, the more I realized it is about a country that decided 20 years ago to bet everything on a specific vision of the future. And that bet is now paying off in ways that are getting very hard for the rest of the world to ignore. The 700 km/h capsule is not a train, not yet. But the technology that made it work, the magnets, the guidance systems, the braking, the precision control, all of that is real. It has been tested, improved, and tested again. And the country building it has already shown, 50,000 kilometers of track at a time, that when it commits to a way of moving people, it does not stop. If you made it this far, thank you. and hit subscribe if you want to see more like this. I want to know what you think about something. If a shift this big in how humans travel has been building right under our noses, what other changes in technology do you think are happening right now that most people are completely missing? Drop your answer in the comments because I will be reading every one.